sheets. Okay. All right, so I put this document as a PDF so you can actually read it on your Chromebooks. I put this up on the Google Classroom. This is really good for you guys to go through. It talks about like stuff like, you know, when they say name specific elements and compounds, like name reactants or name products, don't use the word it, okay? Write reactant or product or, you know, that sort of thing. So make sure that you're reading through their hints here. They're good not just for chemistry, but they're good for a lot of other AP type exams as well. Just generalizations, making sure that you're talking about things precisely. Some of the vernacular, you know, that sort of thing. So be careful with that. Then they break it down based on specific units. So here's unit 1, like period. You know, write period, don't write shell. Ion, electron configurations, you know, remove from the inner shell, don't say that, remove from the valence shell, or, you know, that sort of thing. So read through these for specific examples. And then they give you a practice problem here. And then they go through the answers with those and like, you know, notice this, and this is how they're doing these point values and that sort of thing. So that takes you through unit 1. And then they do the same thing for unit 2 and unit 3, all the way down to unit 9. So I'm not sure if we're going to have time to get through this whole document as well. And so it would be really important for you guys to spend some time on your own going through this. Again, it's going to benefit you in a lot of different ways. So this is uploaded as a PDF on Google Classroom. I uploaded it today. You should see an announcement in your email about that. So then getting back to this guy, this is where we left off yesterday. We were talking about properties of IMFs. We were talking about shapes of molecules. And we had asked, which of the following, did we do this one? Yes, I believe we did this one. C had the highest vapor pressure because it's going to have the lowest IMFs. Bonding and electronegativity then. These are considered ionic bonds. We did this one too.
The board's not on.
Good grief. I always forget that. Oh, we did the most polar one as well. Let's see, ionic, we talked about repulsion. Sea of electrons, we did all of these. Structural components. I think we did this one too, Coulomb's law, because I remember Austin talking about that yesterday. We did substitutional interstitial alloys. Talked about that one. And we did that one. Seems like we were through. Yep, we left off, I think, at big idea 3. Is that right, Austin? You were with me yesterday? I don't know if you did.
Yeah, I'm pretty sure.
Okay. We talked about, no, we did start in on these acid-base reactions. We did this net ionic. Did we do this net ionic? Did we do this?
Yeah, I think we did.
Oh, that's what I thought.
I can't remember exactly where we got to.
Okay, I don't think we did this. I can check the video from yesterday, but I don't think we did this one. So start in on this one. If it looks familiar once you started in on it, let me know, but I think this is probably where we were at. What evidence? So yeah, we did talk about this one. We did talk about that, and then what evidence would be, and then we talked about the evolution of a gas, and then I think that's where we left off, because it doesn't look like we go beyond that. In here. Okay. All right, so that's where we're at, is what is the percent yield of CO2 if you originally heated 10 grams of copper carbonate and captured 3.2 grams of carbon dioxide? So what would your percent yield be here? A little stoichiometry going on here, huh? Welcome back to the Stoic. This one, you guys are going to have to do some calculations. When you're ready.
I think I got it. I just forgot how to do percent yield.
Okay, so percent yield is actual, which is this amount, divided by theoretical. So you have to take this guy, you're going to have to divide him by his molar mass. Once you have his molar mass, then you can figure out that's going to give you the moles here. So divide this by molar mass to get your moles.
Mm-hmm.
Then, because this isn't a 1-to-1 ratio,
The moles would be the same.
and that's going to be the same number of moles here. Multiply that by 44, which is the molar mass of this guy.
Mm-hmm.
And that's going to give you the theoretical moles. So put 3.2 divided by that theoretical mole amount.
Okay.
Okay. So here's the molar mass for copper 2 carbonate. Okay. And this is where they did the 1-to-1 ratio. And then they're multiplying that back out to get the grams of carbon dioxide that should be formed. Okay. So you're going to take that divided by that, and that's going to give you your 90% with sig figs. Okay. All right. How could we improve the percent yield? Well, if we think about Le Chatelier's principle, right? Okay. If we think about Le Chatelier and equilibrium, what's the only thing that's going to be part of that equilibrium constant here? And why?
Wouldn't it just be the CuO? Because no. Oh,
Which one of these is not like the other?
the solid, yeah.
So this is a solid and this is a solid. Remember, solids are not included in the equilibrium constant. So Le Chatelier doesn't apply then. Okay.
So it'd only be
So we want to generate more of this. We want to shift this reaction this direction. So if we change our pressure in our system here, okay, which way would generate more for the product side? So, and you could also reheat it, okay, and make sure that you have the copper carbonate. So there's several different ways that you can improve that percent yield. You could modify the pressure so that we're generating more moles of gas this direction because you want to shift it this way. Okay, so shifting it this way, you're going to increase the moles by reducing the pressure. It would want to make more moles of gas. Okay, all right. So here we've got this guy. You've got your formulas up here. Remember, they're not going to make you write formulas on this because they figure that you already know how to do that. So don't worry about that still. But you still need to be able to do the stoichiometry. So here is your information. See if you can figure out the limiting reactant. What's the maximum mass of H2SO4 that can be formed, and then how much excess is left over. Oh, then if I do it over there, Austin can't see it. Okay.
So for limiting a reactant, wouldn't it be water?
Yep.
Okay. Just making sure I did it right.
And I can show you how I do this. It's different than what they would do it up here. I can insert a new blank slide here.
So if I did it, so how I did it was I found the mole of aluminum and mole of water, and whichever one was lower was the one that I chose would be limiting. Would that be a correct way of kind of looking at it?
Well, you've got to look at that cloud though, because this is in a 6-to-1 ratio.
Yeah, I factored in the 6.
Okay.
When I was dividing
That's fine.
10,
Yeah.
yeah, when I was dividing 10 for water, I multiplied 18 for the molar mass by 6 to account for that. So, got the right answer at least.
150.16. So I'm going to divide 150. What was it? 150.56? Was that what the molar mass of this guy is? No, nobody going to help Lippy? $150.16. Yeah. Okay. So if I take 150.16, so 15 divided by that, that's going to equal, let's just say 0.1, just to make it easier, right? 15 divided by 150, yeah, 0.1. And then 10 divided by 18. So that is 0.56. So I got 0.56 moles of this. I got 0.1 moles of this, but I need to divide this by 6. So that's 0.0922. 0.26 moles of water, and this would be 0.1. So this is going to be my limiting reactant here. Okay, remember how to do that stoic? And then they asked, oops, wrong slide. What is the maximum mass of H2S that can form? So H2S, we would have this many moles times 3, so 0.09 times 3. So that's going to be 0.278 moles of that. Did they ask moles? Is that what they asked? Mass. So I got to do that times 32, 33, 34, 34.1. I get 9.47. Oops, wait a minute, 9.472. We want to keep 4 sig figs. And that's grams H2S. Make sure that you are putting units on everything. If you guys put units on, if you put units on wrong, they mark it wrong. Okay, so be careful with that. And then how much excess reactant is left in the container. So I would end up with 0.1 minus 0.0926. So 0.1 minus that, and we're going to multiply that times, that was aluminum sulfide, so that's 150. So 1.111 grams of Al2S3. Is that what you got for your answers? Good. Just make sure that everything checks out on their end. All right, good. I still know how to do stoichiometry. Austin, how'd you do, honey?
Very good. I got it all.
All right. This is the same one, I think. Yeah. Wait, oh, wait a minute. Oh, this is just the before change after approach that I do. Okay. They just had separate ones in there. So pure sample of copper is heated in excess oxygen. Design an experiment to quantitatively determine if the product is CuO or Cu2O, and then design a plan to prove experimentally that this reaction illustrates conservation of mass. So if we talk about this guy, you would find the mass of the copper. You're going to heat it in oxygen to a constant mass. Subtract to find the mass of the oxygen when combined, and then compare those moles. So you do, essentially, you're doing empirical formula lab, okay? And then here, find the mass of the calcium carbonate, seal it in a rigid container, evacuate the container remaining gas, heat that, take pressure readings along the way, and using their PV equals nRT, calculate the moles of CO2 present in the container and compare it to the molar relationships. All right. When tin is heated with a concentrated nitric acid, the resulting mixture is strongly heated. The only remaining product is an oxide of tin. Student wishes to find out whether this is tin 2 oxide or tin 4 oxide. They have this material. How can you use the data, law of conservation of mass, to determine the following formula? So this is empirical formula data, go.
I think I got it.
Got it? Okay. So first of all, you're going to determine the moles of tin. And then you're going to subtract the mass of the crucible from that after the third heating. Then subtract the mass of the tin from this guy to get the mass of the oxygen. Then you're going to determine the moles of each of those things and set them, divide by each one, and then that's going to give you your empirical. Okay? All right. Bronsted-Lowry then, when we talk about Bronsted-Lowry, this is the only one that we mess with in AP. There is an Arrhenius model for acids and bases, and there's a Lewis model also out there. Arrhenius is kind of like discounted. They don't really do much with him anymore. He's just kind of arcane. If you get into college, they will probably do stuff with Lewis acids and bases, but you don't need to worry about that at this level. Okay, just want you to be aware of that in case you ever hit on that. So Bronsted-Lowry looks at who's donating the hydrogen. So I always tell you guys to find the two pairs that look alike. So look at your anions, see how they match up, okay? Then look to see which one of those pairs has more hydrogen, and that's going to be your acid. The other one will be your conjugate base. Then here, look at these two. See how these anions match up? Find which one has more hydrogen. That's your acid. On this side, it's called conjugate. So this is a conjugate acid. On this side is going to be your base. Remember, some compounds can be amphoteric, meaning that sometimes they will donate a hydrogen, and other times they will accept a hydrogen. So they can either act as an acid or a base depending on the situation that they're in. And water is our classic example of that. Okay, so they're designing this experiment. The reaction is represented with this equation. They're going to place 2.24 grams of sodium hydrogen carbonate in a flask. They're going to add 60 mils of the acetic acid. Then they observe bubbles that form. Okay, what are those bubbles made out of, by the way?
CO2.
CO2, right? It's the only gas listed up here. So they're going to observe those bubbles, and that the flask is going to get colder. So if the flask gets colder to them, if they're feeling that, what type of reaction was this? Endothermic. Good job. Okay. So then identify the reaction above as acid base, precipitation, or redox, and justify your answer. And since we're in the acid-base area here, you can probably identify this pretty quickly as an acid-base reaction, okay? Weak acid is going to react with a weak base here, and they're going to donate protons, or you could say that no precipitates were formed and the oxidation numbers didn't change, so it's not redox. All right, redox, oil rig. Okay, there's also Leo goes GUR, but I use oil rig because I just like that one better. Remember, this is when we're transferring electrons instead of protons, okay? So here we've got these half reactions that we have to look at, and you should be somewhat familiar with these because we did have to kind of cover this a little bit when we did thermochem at the end. So zinc ions are going to react with aluminum metal in the following reaction. Based on this chemical reaction, how many moles of electrons would be transferred when 1 mole of zinc 2+ ions are consumed? You have your sheets, Joe? Austin, you can chime in on your little, okay, he has, all right. All right, let's check our answer here. The correct answer is C. 2 moles for each zinc ion. 2 electrons are needed to convert in the zinc atom. We're consuming 1 mole of zinc, transfers over. All right, redox titrations then. Remember we did the redox titration. This is the potassium permanganate that we did where we turned it that pink color, looking for that very faint pink color. Common misconception, boiling water makes H2 and O2. That is not the case. Remember that covalent bonds are not broken during phase changes. Also remember that temperature doesn't change during a phase change. I gave my pre-AP kids their test today and yesterday, and I've got several of them still telling me that during a phase change the temperature changes. That is not the case. Okay, remember we're just reducing or reestablishing those intermolecular forces. All right, energy changes. These are common graphs that you'll see on the AP exam. If the products have less energy than the reactants, then this is exothermic, and if the reverse is true, then this is endothermic. This is going to be your energy absorbed. This is your energy released. This is your activation energy, is the energy between the reactants and the top of this peak. So if your reactant is here and your peak is way up here, that's going to be your activation energy. A catalyst then will reduce this activation energy. That's the purpose of a catalyst. The catalyst will also sometimes make this, instead of a one-step reaction, we'll make it a multi-step reaction. So keep that in mind. You may have 2 activation energies. Okay, so try to figure out the cell potential of galvanic cell Z. I think this one was one that we already did recently, so I don't know. Probably shouldn't have spent much time on this one. I think we already did this. Isn't this the same one that we had from our practice test? Yeah. So I'm just going to zoom through this one. This was the B, where you had to subtract these 2 values. And I think we talked about this one too. Yeah, we did this one as well. So I'm not going to spend time on this. You can go back and watch that other video if you want. Okay. Okay, so while cleaning up an experiment, the student wishes to dispose of the unused solid I2 in a responsible manner. The student decides to convert the I2 to I- ions. They have access to 3 solutions and a standard reduction potential table here. Which solution would the student add to I2 to reduce it to I? And circle your answer below and justify using calculation for E naught, the overall reaction. Remember, we want our value to end up being a positive value. We need to have, your cation minus your anion. So which one of these would be your cation minus your anion, if that would work, and how would the math balance out for that? And then they want a balanced equation for that part. So let's do this part together first, and then we'll break and do this part again, because that way you've got the right equation in case you get this one wrong. But remember, if you get this one wrong and you can still show the proper net ionic equation balance, they're going to give you points for this part. So don't just quit here, like circle 1, and at least if you lose the points there, you won't lose the points here. So keep that in mind, because they will carry those, that material forward. Ready to give it a go? Okay. All right. So this is the one that should be selected, the S2O, okay? Because if we take this guy minus this guy, we're going to get a positive value here. Okay, remember we need a positive value in order for this to work. And then, they showed us the balanced equation. So this would be what that balanced equation would end up looking like. Okay. here's another one. We've got molar mass of an unknown metal M. It's going to react with iodine and excess metal to form water-soluble compound Mi2. It's represented in the equation above. The reaction then proceeds. All I2 is consumed, and the Mi2 solution is collected, heated, and the water removed. So this is that table. So given that metal M is in excess, calculate the number of moles of I2 that reacted based on this data. This would be an example of an FRQ question, one of the longer ones probably, where they're going to have you do a bunch more stuff with this. You ready? No? More time? Okay. know when you guys are ready. Good? Okay. So, again, they're going to give you partial points. So if you can figure out this much, like how much I2, then you get a point, okay? Number of moles of I2 equals the number of moles of M. They're going to give you another point for that, okay? And then you can turn that into grams per mole, figure out the molar mass of that. So you get the grams here per the moles of material that you had. That's going to give you your molar mass, okay? All right, kinetics. Just real quick, see how much of this we can get through. So kinetics was kind of a new thing for us this year. That's nothing that we've really touched on in prior years. I've talked a little bit about catalysts today. I think some of this makes sense, like more reactants, you're going to have more collisions. Temperature increase in kinetic energy is going to give you more collisions. And then greater surface area is going to affect your rate of reaction as well. Okay. So they're designing an experiment here to study the reactions between sodium hydrogen carbonate and acetic acid. The reaction is represented by this reaction above. Again, they're placing these 24 grams in 6 mils. They want to identify the reaction represented above. We did that already. We identified that. Student observes bubbling as rapid at the beginning of the reaction and gradually slows. Explain this change in reaction rate in terms of collisions. So as you are using up this material, there's going to be fewer collisions happening because there's less of this material to collide with each other. Okay. All right, rate order. Remember, we had rate order. So when A is doubled, the rate doesn't change, so that's going to be 0 order. So remember, you have to look for a situation where B is held constant. If this is doubled and this doesn't change, it's 0 order. Here, A is held constant here and here. This doubles our reaction order, so this is going to be first order reaction. Okay. Remember these lines. If we have a 0 order and we have concentration versus time, and that's a straight line, that's 0 order. If the natural log of concentration versus time is a straight line, then that's going to be first order. And if 1 over the concentration divided by time is a straight line, then that's second order. And they will oftentimes show you graphs like this and get you to try to figure out, what's going on here. So we've got these 3 different graphs here that are drawn. This is set up so that you could determine if this was a straight line, it would be 0 order. If these were straight lines, it would be first order. And if these were straight lines, it would be second order. Okay. So you're going to use, you're going to use the plotted graphs to determine the order of the reaction. And then the initial rate of the reaction in trial 1 is 0.001 moles per liter seconds. Calculate the rate constant for that reaction. So how would we do that? Well, we would determine that this is a second order because, like I said, this line is completely straight. So you should be able to identify that and go, oh, that's second order. Okay. This one, there's a slight curve to this line. This one, there's a definite curve to the line. So those are out. Then if you remember that we had this equation, rate equals K times the concentration, we have to square this because our equation was squared. It didn't come off very well, but we've got a coefficient 2 there that's in that. So we've got to square that. And so we're going to solve for that and get your answer. So that is where we will leave off for today. We will start talking about first order reactions mañana. Good?
See you, Lippy.
Bye, hon. See you tomorrow. Oh, it was almost oh, that's where I left off. Where did I leave off? This is so slide 82 is where I left off. 82. 82. Should write that down this time.